Okay, so as I said, for a computational scientist, it's important to know something about the computers. You see that um, we need reasonable amount of information about memory, CPU power. That helps in designing a solution, which kind of problems you can solve in a computer. So it's important. That's why I will just cover basics of computers and software before you go on to Python. Okay, so to begin with, it's called von Neumann architecture. So it has, computer is basically has three important components. Okay, so this is abstract. Von Neumann was a mathematician. So he said there are three components in a computer: a computation unit, which does the computation, like adding numbers uh, and all that. Okay, logic operations. There is a memory where data is stored, and there is an input output. That is, I need input for example temperature of the atmosphere, so all that should go in, or keyboard. So how do you enter a program in a computer? So you do a keyboard. So that's the input device. Output is, it gives results. So we put results in the screen of the computer, or send it to the printer. So these are our output devices. Okay, of course there are tons of, these are only characteristics. Like camera is an input device. Okay, speaker is the output device. So you can classify the input output. Anything other than memory and computation unit will be coming into this category. In any case, so let's see basically what is there in a laptop. Okay, now in a more advanced computers like servers or supercomputers have essentially the same design, but of course the components are more powerful inside a server or in a supercomputer. Okay, so here in a laptop, if you open the laptop, you'll find this is what we'll get. So of course you can't make out much on this, but I few things like battery is visible here. This is an Apple laptop. I took an image from this website, and the CPU is sitting, the processor is sitting below these two fans. Okay, the two processors, so they are sitting below that, and the RAM, a memory called random access memory, is sitting here. Okay, so I'll show you in a schematic diagram. So this is not exactly how they're wired, but this is schematic diagram. So this thing is called motherboard. Okay, so in fact this is a motherboard. Battery is somewhat, is kind of attached to the motherboard. Nowadays everything is sitting on the motherboard. Earlier hard disk was outside the motherboard. Now hard disk sits on the motherboard in the more recent computers. So hard disk will sit on the motherboard. Also it's called logic board. Okay, logic board or motherboard. So this is a processor which is sitting below below the fans. Now this is a memory. So we got a memory device here. Now they're connected via wires. So memory will send data through these wires to CPU. Now this memory is a random access memory. So random access memory is where all the data, I can reach any location of the memory by giving the address in one shot. This is random access. Now, of course, this memory is temporary. That means whatever is stored here will disappear when machine is powered off. If you want to save the result permanently, then you need to put it in a hard disk. So the two types of hard disk, one is called hard disk, the second is SSD, silicon drives. So SSD are more expensive and less capacity, but hard disk are more capacity. Okay. Now, again, these are wires. The black lines are wires. Now, to talk to outside world, we have I/O controller. Okay. So this controller will take input, and of course it'll take instructions from the CPU. CPU will tell, okay, get input from the keyboard. So that's how this I/O controller will talk to CPU and the device. It will also talk to this memory also. Sometimes memory, it can write directly to the memory. Okay, so this how it is connected. Now Battery is here, so battery powers all the units. Okay, so battery will be connected to this stuff. Anyway, so this is a schematic. So please remember what we wanted. This is a computing unit, which is where processing will take place. This is memory. This is also memory, and we have I/O here. Okay. Now there is some memory inside CPU itself. Okay, so memory comes in hierarchy. So this is slowest memory, then this slightly faster than hard disk, and even faster memory is closest to the processor. Now I give the example, like if you want to get some reference, you go to the library for a book. Well, it takes more time. No, you go to the library. So library is like hard disk, is there. Now I want quicker access, and I keep in my office. So I have it, or in your house you keep the book. So that's like memory. Okay, by the way, but please don't make one-to-one analogy. It's not that I power off and in distance wise I'm saying like library, then home. But if you want even faster access, then I can keep it close on my table. So table is like it's called cache. So it is close to the CPU. So these are three types of memories. Okay. Now, if you look at inside the CPU, modern processors, this is one of the AMD processor called ROM processor. Okay, this name is EPIC 7002. Now this is a well, now new processor is coming, which is even better than this. But this is the fastest CPU processor CPU available right now. So how many computing units does it have? So CPU itself has many computing units. So CPU's computing units will add. It can do some logical operations. Each unit can do on its own. So it has 64 cores. Core is a computing unit. Okay. So how many? So 8 cores sit inside this block. So there's 8 more. So there are 8 such blocks, and each of them have 8 cores. So 8 times 8 is 64. Okay. And there's a memory called L3 cache. So L3 is written here. You can see that L3 cache is very close to the CPU. Of course, CPU had its own memory called registers, which is the fastest. So there's another one which is really fast, which is close, which is inside the core. Okay, but anyway, beyond register, this is called L3 cache, which is outside, but it is in this block itself. Okay. Now these cores talk with other cores. I mean, this block talks to other block via this central place where itself has some memory. Okay. It's called L1 and L2 cache. So there are 3 levels of cache right now: L1, L2, L3. L3 is the fastest, but L1, L2 cache is sitting here. All right. Now, so this is another memory which is that. Now, CPU or rather RAM sends the data here. Okay, so it will send to L2 cache or L1 cache. Okay, and that will go finally to a register or L3 cache here. Okay, so that's how it is organized. Anyway, you don't need to know much more than this for this course, but it's important if you write optimized code. Sometimes we need to understand the cache size. All that becomes useful for very optimized code. Now, this is a block. This one blue block has been enhanced here. You can see core 0, core 1, core 2, core 3, and these are the caches here. Okay, sitting here. So, I mean, people are trying to pack more and more computing power within a CPU. Okay? Please remember, the CPU is its size is basically something like my thumb size. Okay? This is a CPU size. And within CPU, all these things are sitting there, like the billions of transistors. Okay, now all these are automated and very sophisticated machines make all this stuff. But as a user, we need to know basically how they are organized. We need this nomenclature for all sorts of computing literature. Now, so right now I'm written here about memory. Okay, kilobyte. So kilobyte is, so 1 bit is 0 and 1. So 1 bit, and 1 byte is 8 bits. Okay, I'm sure all of you know this, but I'm just repeating this right now. But what is important right now is kilo. kilo is 10 power 3, but in computer we work with 2, power of 2, right? So that will be, so because access is you need to generate address, but there will be, the number will be 0 1 0 1 1 1 like that. Okay, so my number in computer is basically binary, and I'm going to discuss a bit in today's class only, a bit later. So just bear with me. So it's in binary, but so it's going to be 2 to the power 10. Computer will see 2 to the power 10, but 2 to the power 10 is 1024. Now in decimal, 1024 is not something convenient for me. You know, 1024 is 24 makes it. If I multiply 1024 into 1024, I mean, I can't do it in my head. But we can approximate as 1000. Okay, so that's why it's 10 cube, is approximate. Mega is 10 power 6, but in computer it's going to be 2 to the power 20. And you see M symbol here. Tera is 10 power 12, and it's a 2 to the power 40. Giga I forgot to write here. Giga is 10 power 9. No? So giga is sitting here. So GB is also important. I didn't write it here, but giga is important here. Now peta is 10 power 15. Now in supercomputers we have memory of this size. Your hard disk typically will be on gigabytes. Okay, 10 power 9. But peta is 10 power 15. Now exa is even bigger. Exa is right now we don't have exabytes of memory in computers, but it is going to be 10 power 18, and that is what is target right now. I'm going to show you a bit later how much is the computing power of a machine. It is we are targeting to get exa computing that will be doing 10 power 18 operations per second. Okay, no computer is able to do it right now, but we are close. I mean, the world is close to 10 power 18 operations per second. Okay, so these numbers, please remember: kilo, mega, giga, tera, peta, and exa. Now let's look at this ROM processor, which I just described, which has 64 cores. So each core can do many operations per cycle. Now what is cycle here? Floating is real. Okay, floating is like 2.5 multiplied by 3.5. That's called floating point. Computers can also do integers operations, but as a scientist or physicist or engineers, we basically work with real numbers. Okay, so that's why floating point operations is important. Now, computer also has a clock. Okay, there's a clock. In fact, it's outside the CPU, and the clock is synchronizing the CPU, memory, I/O device. All that is synchronized by the clock. So when the clock tick happens, then you'll send signal. Okay, if you want to send data, send it now. Okay, so it basically clock is like a heartbeat, and it is able to synchronize the whole computer. Now, in one clock cycle, you might expect that it can do one operation, right? Multiply two numbers or add two numbers. But it turns out, because there's enough number of memory and enough number of hardware, it can do 16 real operations. Because it can multiply 16 pairs of numbers, or it can add 16 pairs of numbers. Okay, so now I'm assuming that this processor is 2.5 gigahertz, the ROM processor, but some other processor may have slightly higher clock rate, or some may have even a bit less. But in any case, 2.5 is for the ROM processor. So 16 times 2.5 operations, giga operations. Okay, giga is 10 per 9. That many operations it can do per second. Okay, so you multiply 2.5 10 per 9 multiplied by 16, that will be 40 times 10 per 9. So ideally it can do 40 giga floating point operations. The FL is floating, OP is operations. Okay, so ops. Okay, so giga floating point operations. So it's huge, 40 times 10 per 9. But that is for one core, but I have 64 cores. I have 64 workers inside the CPU. So if I multiply 40 with 64, then I get 2.56 teraflops. Okay, so it can do 2.56 times 10 to the 12 floating point operations per second. In practice, we do not get this many operations done because of various factors, but these are peak performance. Okay, one can expect. Well, we don't really expect, but anyway, this is a peak power of the CPU. I'll tell you a little bit later why we can't do it, because well, I can also tell you right now that CPU is very powerful, but the data coming from RAM, it is not coming at this pace or at this speed. Because these channels are a bit slow and memory also is slower to data transfer. So memory access is a bottleneck. Otherwise, it can do all these operations per second. Now, nowadays there is a new computing device called GPUs, okay, graphic processor unit. This was a device made for graphical applications like rendering of videos. No, so your television has a GPU sitting inside them, okay, but it turned out at some point, some 15 years back, these engineers thought that one can use the GPUs to do supercomputing. So it is right now being used. In fact, is heavily used. The IIT Kanpur's best machine has GPUs in it, and in fact, it is best because of the GPU. Okay, so in future there will be more and more machines with GPUs, and so one GPU is made by many companies, several companies, not many companies, but so NVIDIA is one of the leaders of this this architecture or this hardware. And well, I mean, you can't make out, but this is how this GPU card looks like. And it's also very heavily used for artificial intelligence and machine learning. Okay, so Google is using tons of these GPUs for its AI applications. Okay, now the fastest GPU right now is A100. Okay, right now that's what NVIDIA is selling. AMD is another company, also has a GPU, but okay, so it has a different name and all that. Now, if you look at compared to now, you don't need to look at all the numbers, but just look at how many cores are there in a GPU. So A100 card has computing core is 6912. Okay, so compare 64 of Rome processor, which is the fastest processor. Compared to that, we have 100 times more CPUs, right? Even more than 100 times. So, but these CPUs are not as these cores are not as powerful as a Rome processor. But if you program well, it can really give you good performance. Okay. Now remember, we had double precision. Okay, double precision I'm going to tell you a bit later. Just don't worry right now. So double precision is that operation was 2.5. No, sorry, 2.5 teraflop. Now this one can do 4 times more. It's 9.7 teraflops. Okay. So this card it has 4 times more performance than a Rome processor. So that's why people are using such cards for real supercomputing applications. Okay, if I do machine learning, then I can even get much better performance, like 125 teraflop. Okay, so that's how we need these numbers. Huh? What is the power of this machine? And you need to know from the flop rating, how many floating point operations can it do per second. Okay. So you see, immediately you can see that you need to know something about the machine to choose which machine to use, how to write your code. Of course, the Python codes do not automatically run on GPUs. You need to do something more. It runs on CPUs, but not in GPUs directly. So you require a bit of more advanced skills to use this GPUs. Okay.